now we want to investigate the issue of phase changes and in general there are two ways that a substance can change phase. Number one is from a solid to a liquid, or conversely from a liquid to a solid. In the solid to liquid case you're gaining heat, and in the liquid to solid case you're losing heat. So the solid liquid barrier, but we also have the liquid to gas as well. And if we're going from a liquid to a gas, then we're also gaining heat. And if we go from a gas to a liquid, we're losing heat. So these two changes, from a solid to a liquid or a liquid to a gas, your substance gains heat, and when you move from a liquid to a solid or from a gas to a liquid, you lose heat. Okay? Now, the boundary between a solid and a liquid is the latent heat of fusion. Okay? It's the latent heat of fusion. Whereas from a liquid to a gas, or a gas to a liquid, we call this the latent heat of vaporization. Latent heat of vaporization. Okay? This is often denoted by L sub F, and this is often denoted by L sub V. Okay? Now, the total amount of heat, okay? The total amount of heat, the units on your latent heat of vaporization and your latent heat of fusion are going to be energy per unit mass. Okay? So these have the same units, energy per unit mass. And in the SI system, this is of course going to be joules per kilogram. Sometimes it's reported in kilojoules because these values tend to be fairly high per a given substance relative to their specific heats. Okay? Now, you might be wondering, why don't I have a delta T in here? Why no delta T? And this is because when a substance, let's say we're freezing water. Okay, let's say we're freezing water. So to freeze water, I have to cool the water down to 0 degrees Celsius. And if I'm going to assume a uniform process, then I cool all of the water down at the same rate. Now, this doesn't physically happen, say in your freezer. If you take a transparent cup, right? If you take a see-through cup, don't do this with a glass, but if you have a plastic cup that's see-through, or like a sports bottle or a water bottle or something, and pour maybe halfway into the bottle and leave the cap off, okay, or the end open if it's a cup. Leave the end open and set it in the freezer flat and take it out every, say, 30 minutes or so. And you'll notice that the water tends to freeze from the top down. It doesn't freeze uniformly. That's because energy is escaping more easily from the top than it is from the sides. Now, if I were to close the top and there were no energy transfer um, from any one part of the surface of water more than any of the other parts of the surfaces of water, then it would freeze uniformly. But in any case, right, so we're going to assume a uniform freezing process here. And the first step is to cool our water down to 0 degrees Celsius. And then once the water is at 0 degrees, then as I continue to expose it to the cold temperatures, it will freeze. It will go from liquid to solid at 0 degrees. Okay, so there's no temperature change to move from a liquid to a solid. It's only a phase change. I'm only changing the type of matter. Okay, I'm moving it from a liquid to a solid. Or if I want to take a block of ice and I want to supply some heat to it, I'll be taking a solid to a liquid. But in any case, okay, this is purely dependent on the amount of mass. So the amount of heat that it takes to change the phase of a substance purely depends on the amount of that substance you have. And if you are a college student, you should know this because it takes any given stove a much smaller amount of time to boil water for ramen noodles, your 2 cups of water there, as opposed to boiling several cups of water for a large batch of pasta, right? If you're going to boil lots of pasta noodles, it takes a long time for the water to come to a boil in a big vat or a large saucepan because you have a lot more water. And so it takes more energy for all of that water to reach the boiling temperature. And so this is just purely a function of mass, okay? So these latent heats of fusion and vaporization have specific values that are given experimentally, and they're given in your text. So I won't belabor those points here, but we will do an example here. And let's bring up a blank board here. And let's suppose that I want to vaporize 100 grams of water. Now this water is at an initial temperature of 100, so it's right on that cusp. Okay, 100 degrees Celsius. And I want to know, okay? I want to know how much mass of copper okay, what mass of copper initially at 700 degrees Celsius, so your metal smithing, say, is needed to vaporize all of the water. So I'm only going to bring in just enough copper to fully vaporize all of the water. Okay, so this is not a very smart smithing technique, by the way. You definitely want more water than will vaporize when you stick a hot piece of metal in the water. But in this case, we're only going to, we want to vaporize just this specific amount, right? And the water's already hot. So the heat gained from the water so this is going to be the latent heat of vaporization times the mass of the water and the heat lost by the copper. Now this is just going to be our familiar MC delta T. So if I vaporize the water, I'm also going to assume, okay, assume final equilibrium temperature. Okay, I'm going to assume that the copper, all of the copper, goes down to the temperature of the water that just vaporized, or 100. Okay, so this is going to be the mass. This is going to be the mass of the water. This is going to be the mass of the copper. This is the latent heat of vaporization of the water. This is the specific heat of the copper, not the water. And our delta T is going to be 700 degrees Celsius down to 100. Okay. Now, again, assuming that no heat is lost to the environment in the exchange and that all the heat from the copper goes into the water, under that case, then the heat lost by the copper plus the heat gained by the water must be 0. Okay? This is just a conservation of energy statement. And so what that means is the heat gained by the water must equal the heat lost by the copper. And so we have the latent heat of vaporization. I'm going to drop the W subscript because we only have one thing that's vaporizing, times the mass of the water. It's going to be equal to minus the mass of the copper, which is what we're going to solve for, times the specific heat of the copper multiplied by the temperature change of the copper. Okay. Now delta T is, actually my delta T up here is wrong because I need final minus initial. So this needs to be 100 minus 700. Okay. So this is 100 minus 700. So that means this negative sign this minus sign makes that do that. And so we have the latent heat of vaporization times the mass of the water is equal to mc cc delta T. And if I solve this for the, really what I should do is I should put that, okay? This is the absolute value of the temperature change. And so in doing that, now I can solve for the mass of the copper. It's just going to be the latent heat times the mass of the water divided by the specific heat of the copper times the absolute value of the temperature change. So this is going to, now, there are tables in your book that give the latent and specific heats, the latent heats of vaporization and of fusion. And when you look up the latent heat of vaporization of water, you'll find that its value is given as 2,256 kilojoules per kilogram. Okay? And we're going to multiply that by 100 grams, or 0.100 kilograms. And I'm going to divide this by the specific heat of copper, which from before was 387 joules per kilogram per degree Celsius, multiplied by our temperature change, which is going to be 600 degrees Celsius. So notice what happens. These kilograms cancel with those kilograms. We're going to do the calculation in joules, but these units of energy cancel out with those. These cancel out with this, and I'm left with 1 over kilograms, or just kilograms. Another thing that I could do is just cancel the kilograms on the bottom here and the kilograms on bottom here, and I'd be left with the kilograms up top from here. But in any case, no matter how you work out the units, it comes out to kilograms. And when you run this calculation, noting that this is in kilojoules, so this is actually 2.256 times 10 to the 6th joules. When I do that, I come up with a mass of 0.97 kilograms. So if I have a block of copper that is 0.97 kilograms in mass, and it's at an initial temperature of 700, okay? It's at an initial temperature of 700. And all of that energy goes into vaporizing the water into steam, then I need 0.97 kilograms in mass. Now, in truth, is that going to happen? No, okay? There's a few things that are going on here. Number one, you won't ever get a pure process. Some of the energy is going to escape in the environment. You're not going to be able to vaporize all of the water that way. Further, and more importantly, actually, you can then raise the temperature of steam. Okay, steam doesn't have to stay at a temperature of 100 degrees. And steam actually has its own specific heat. So really what would happen is, assuming, okay, the energy from the copper goes into vaporizing the water. If there's any energy left over, right, after the water has all been vaporized, then any energy left will go into raising the temperature of the steam, and that will further lower the temperature of the copper. But it won't be below 100, right? So I guess what I'm saying is your initial temperature change for your copper is not going to be 100 degrees, or 600 degrees. The change is not going to be 600 degrees. Some of that energy from the copper is going to go into vaporizing some of the water. If there's any energy left in the copper, once the water is completely vaporized, then that excess energy will go into increasing the temperature of the steam. Now, if you don't vaporize all of the water, right? Let's say you don't vaporize the water, then what will actually happen is that your copper will simply decrease in temperature until the amount of heat gained by the water is equal to the heat lost by the copper. Okay, so those are the physical processes that are going to be happening. I think we'll leave that there, and we'll talk about conduction, convection, and radiation in the next video. So sit tight.